this talk last year as well for Halvor's class, and I've done some minor changes and added one slide at the end because I, as everyone else, has sort of grown over 1 year. But yeah, if I'm going to highlight some possible errors, if you're one of the people who are way ahead of everyone else and sort of spot the errors immediately because you know how the C++ language functions, please don't shout that out, because I want to see if sort of the other people might pick up on some of the nuances. It won't be that many, it will probably just be like one. Right, and then, you know, my internet does not seem to be properly working. Good to go. So yeah, C++ new was what we sort of gave it as the title last year. We're going to show some cool C++ 11/14, mostly 11 stuff. Give you just a sort of short introduction to the C++ standard library and some sort of general things that you should keep in mind. Afterwards, it's some typical mistakes that we've seen people sort of head into when they do the graphics course, followed by some general tips and some sort of good resources where you can learn more. And then the slide on reflection, which isn't listed ahead because I forgot that I had the topics screen. And then sort of general questions at the end, but just, you know, raise your hand or shout out if you have any questions during the presentation as well. Right, so just straight into it. The main sort of cool C++ stuff that I'm going to introduce are just auto and lambdas. The reason is that I'm just going to sort of show how we can use them together with the standard library or the standard algorithms library to do some cool stuff, to sort of just give you a taste of where you can go from there and show you how you can learn more about that. So I guess we can just sort of get started with that as soon as I do the next slide, which is, you know, the standard library. Or, you know what, we'll just do the cool C++ stuff first. So we'll just do this with sort of live coding. Lectures. There we go. So to sort of show stuff up, we have lambdas in the language. Or first we have this thing called auto. So normally you guys have learned to sort of write, you know, int a is equal to 0, and then you create an int and, you know, it's named a, etc. And that requires, you know, typing. In this case, it's sort of a stupid example because you'll never do ints this way. But instead of having to write all your sort of types out explicitly, you can also introduce in C++11 write auto. So auto a or auto b is equal to 0. That will make auto you know, be an integer. So everything here sort of works the same way as it does in normal C++. That will still be an integer, and it will still be sort of declared on the stack. Everything will still be decided at compile time. There's no sort of magic going here. It's essentially just that, you know, when your compiler goes through this code, it will change that auto out with an int. For ints, this is really stupid. Because, you know, it's one more letter to write, and it's actually more cognitive for me because I have to evaluate the right-hand side of the expression to understand that, to know what it's supposed to write there, or what type it's supposed to be there. However, you will quickly get into situations where that is preferable, like if you have a really long sort of variable or type name, or if you know, there's any other situation. If it's really explicit what you're doing, or if it's obvious to everyone, then, you know, auto might be a solution to look at. And there are also some cases where you have to write auto, which is the cases with lambdas, which essentially is, you've learned about functions by sort of the standard way of, like, you know, creating a void function, so print, which, you know, takes, let's say, an integer and then prints it out. However, the other thing that we got in C++11 was this thing called lambdas, which you have to declare by auto, and it's basically an anonymous function. You can think about it as an anonymous function. So it has this weird syntax. So we can say int a, and then we just do cout a, and then we can just call the lambda with 1 and get out of terminal. And I forgot to include the correct headers. Right, cool. So, there. There we are. So, you know, this is essentially the same as just writing print a, except that with this lambda here, we have now sort of created a function that only exists within the scope of main. So it follows all the same scope rules as sort of regular variables. The way the syntax works is essentially you have this capture list here, which I will get back to, and you write sort of the parameters for the lambda function. And then you start with your scope and write what you're supposed to do within the lambda function here. And then you store it, you know, in a variable, which has to have the type auto, because you cannot know the type of a lambda. Is there any questions, or is everything like super clear? Cool. I'm just going to assume that everything is super clear unless anyone says otherwise.
So you guys used lambdas before in the other courses, right? So algorithm data structure for that.
It's not for programming. Not for programming.
Ah, yeah. Okay.
Ah, right. So you use it there. So okay. So then, just quick hands up. Who here is not familiar with the standard algorithms library, like find if, remove if?
I'm not familiar with it.
You're not familiar with it. So who's not familiar with standard string? Who's not familiar with standard vector?
Cool.
Cool. Well, we'll
go through all of it. Go through all of it. Thorough.
Yeah. Okay. So yeah, lambdas. Cool. So the next cool thing about lambdas. So this is what's called a capture-less lambda. It's essentially just sort of, it works the same way as a function. The other cool thing you can do with lambdas is that you can actually, you know, capture stuff within them. So, you know, lambda cap. Wherein I can bring variables from my scope into the lambda. So I can say that I want to take in b. So, you know, we can call this function like multiply. Multiply by b. And then we return just a multiplied by, you know, b. And then we can, you know, cout multiplied by b, you know, 2, which means then that, okay, if we set b to be 2 instead, then we should get 4, hopefully. Yeah, cool. Cool. So that's capture lambdas. These capture by value by default. So you know, just as regular functions, we're not getting b as a reference. We're getting a local copy of b. So if we modify it, that won't change the original b. However, if we want to modify it, you can, you know, take b as a reference with that syntax. So that's lambdas. Sort of that they exist isn't the interesting part. The interesting part is what you can do with it and how it combines really nice with the standard algorithms library. So we can just start with that straight away. Yeah. So the standard library. You know, you've used string before, and I assume, and you've used vector as some of you. We sort of want you to actually use those here in the graphics course. We're not putting that many restrictions on what you're using in terms of the standard stuff. You know, it's preferable perhaps if you not go so cutting edge that we won't be able to compile it. But you know, C++ 14 stuff, and most of C++ 17 is fairly well implemented now, so you can go ahead and use that. None of the stuff that I'm showing now is, you know, 17. It's only 14 stuff, or up to 14. Yeah. So the algorithms library, we can just look it up. So for those of you who don't know, CPP reference, it's a page that you should get used to visiting because it's a really good resource. It takes a while to get used to reading it because it's written like, yeah, it's written in C++ style. So you know, it's not always as easy to follow, but it's still sort of, it's very up to date. It's usually very correct, and it's a good resource once you learn how it functions. So yeah, so this is the main page, and then we go to the algorithms library because we want to look at algorithms to fix our problems. And you can see here that we have a sort of good selection of algorithms available. We have stuff for, you know, checking if yeah, all of, for each, counting, finding the end, searching, copying, moving, filling, transforming, generating, removing, swapping, etc. Rotating, sorting, partitioning. So a lot of this stuff should be familiar to you from the algorithms course. Yeah, binary searching, all of those sort of fun stuff. But the cool thing here is that all of these algorithms are written in a very generic way. So they all have a relatively uniform interface. They all function sort of the same way. And I'm going to show that using sort of 3 different examples. The examples that we'll be looking at is find, findif, and sorting. Yeah. So we'll start with finding. So the reason I'm showing these examples is essentially just because they're relatively easy to show off, and they also show off how sort of uniform the library is. And it's also the ones I find myself using the most. So the way the CPP reference work here, we get the sort of overview of all the different functions available and their signature. And the thing you want to look for is this sort of predicate logic. I'll show it soon. But that basically essentially starts dealing with where the lambda comes in. But before we start with that, we'll do sort of a regular find, just to show how the standard library works. So let's see. We'll start with you know, we'll try to find yeah, the number 2 in a vector. That's, you know, a thing that we can do. So we'll just write a vector of int. So 2 0 9 5 8 5. So you know, we've created this vector which contains some numbers, and we want to find the number 2. We could do that using sort of, you know, a standard for loop, iterating through all of them, just checking if any of them are 2, and then breaking out. However, we can do it a different way using the standard library, using std_find. So what we do then is that we, you know, write std_find, and then we send in the range of the element or of the container, so a.begin and a.end, and then we send in what we want to find. So in this case, it's the number 2, and this is also where auto starts being something you want to use instead of writing the full expression, because now I'll write, you know, auto iterator is equal to std_find. And if I wanted to write that not using auto, I would have to write like std vector of int, and then iterator is equal to std_find ... And those type names can become quite long after a while. And if you change from, you know, using ints to floats, then you suddenly have to go and change everywhere you want to get out that iterator or declare it. So, you know, just use auto. So cool. So the way the algorithms library works is that they take in two pieces of information. They take in they take in a range of elements that's highlighted by sort of the first element and the last element, and then they traverse them from first up until but not including last, which I hope they show off. If we go to the no. No. Okay, well, if we just find the actual iterator, then we can see it because they have a picture showing essentially you're taking a range, which is sort of taking the array. So we're giving them essentially a pointer. In this case, when we're talking about vector, the iterator is actually a pointer, but in other cases you can just think of it as a pointer. So you sort of give it to a pointer to the first element and a pointer to the element after the last element. So it's like size plus 1, so, or size, yeah, from 0 point. You don't have to send in sort of the end of the range. You can do sort of like sub-range by just sending in begin and then sending in the element in the middle, and then you will just, for instance, look in for half the range, or just sort half the range, etc. So it's quite versatile. But once you get the result out, so we're looking for the value of 2, and what we then want to do is to check if it's actually found that value. So we'll do, if the iterator is not equal to a.end, that means that we've found something. Because the way these libraries work is that you send in the end value, and if it doesn't sort of, for instance in the find version, if it doesn't find what you're looking for, it will return the end value that you supplied. So in our case, we'll get back the a.end value. And in that case, we can just print out. And as you can see, you also, iterators in general have pointer semantics, so you'll also like dereference them, etc., to get out their actual value, if they have one. And then again, if we run that, we got a cool, I forgot to include the vector. Yeah, we'll get in out 2, and I'll just go and comment out this bunch. Yeah, we'll get out 2. So cool. So now you all know how to use sort of std find, or any sort of, that's the basics of how the algorithms library work. The more sort of complicated example using, which is where the lambdas shine, is if we say that instead of just finding one single value, we want to find the first value that specifies a specific criteria. So for instance, we can say that we want to find, and this is where findIf comes in, we want to find the first value that is divisible by 2. So here what we'll do then is that we'll supply a lambda to the actual function. And if you go to see PP reference, it says here that one of the versions of the function takes in a unary predicate, and that's just a fancy way to say that it takes a function that it's supposed to return, true or false, or some sort of thing, and that function takes one argument. So if you get like a binary predicate, then that takes 2. Normally you could write, int item, but I'm just always doing, const auto item, and then we'll just return if item mod 2 is equal to 0. And if the iterator, if we actually found something, then we'll print it out, which should mean that we should get out 2, because findIf will only return you the first value of the thing that you're looking for. So yeah, so we'll get 2 again. We can obviously, or we can sort of extend this, so you don't have to hardcode the values. This is where a capture list comes in, so we can have the int value of b, which is equal to 5, and then we can say we want to find whatever is sort of whatever we can model with b. Which is 0. Yeah. So, anyone have any questions about the use of lambdas, or is everything perfectly clear?
How do you compare it to local functions in other languages?
I don't have enough experience with local functions in other languages. Again, it sort of turns into a local function, I guess. The only thing I'm not sure about with local functions is I don't know how other languages deal with captures. I know some people find the C++ syntax to be a bit too explicit there, but I don't mind. There's also another thing you can do, which I would prefer you didn't, which is that instead of sort of saying that you want to bring b into the scope of lambda, you can say that you just want equals or just reference. And what that means is essentially like if I access a variable that is in the outside scope within this lambda, then just bring that in sort of automatically by reference or by value. And I would prefer people not do that, because it's really hard to sort of see where all your variables come from. So try to respect scope and only take in what you actually need. Cool. I'm still taking B, otherwise that won't work. So that's findIf. We can do other stuff as well, so we can remove stuff. And we'll removeIf is the probably second function that I use the most. It's a bit weird because it doesn't actually remove anything, so it's great naming. The reason is that often this this library or the algorithms library, they will sort of modify the elements in a range, but they will usually not they won't modify the container that they're operating on. So if you're doing removeIf, it will sort of prepare for stuff to be removed within your function, but it won't actually modify the container so that they will sort of decrease the size or anything. So what this function does is that it removes all elements satisfying a specific criteria from the range first to last, and returns a past the end iterator to the new end of the range. So essentially it moves all the elements that are supposed to be deleted to the back of the range, and gives you back an iterator pointing to the first element of that new sort of subrange. And what we want to use it with is, since we're using vectors, we want to use it with, we sort of want to remove it from something. So we want to use it with one of the functions that vector has, which is the erase function, which actually removes elements. So we'll just do a.erase, and then we'll do a removeIf. A.begin end, and then we can probably remove you can probably remove everything that isn't an odd number, which will remove almost everything. Cool. So obviously we've now done this. So here's another usage of auto. By the way, you can instead of using regular old for loops with like int I, if you want to iterate over a whole range, you can just do auto reference, or just auto, or const auto reference if you want. And this here will sort of fix the for you, so it will go through every item in the container, so you don't have to sort of do the indexing yourself. So we'll just do that cout item. And then I hope this won't work. Let me do that there. Yeah, which is not exactly the result. So let's see, what we get is that we get, we'll just comment out the two first. The result we get out is we get 20885, which is, you know, to a certain degree correct. It's just that there's, you know, there shouldn't be a 5 there, and we should not have, you know, 2 8s because we didn't have that in the original range. And the reason for that is that there is a bug here, which is sort of really hard to spot, and it's something that you will probably meet. I have met it several times already, which is if we go and read the documentation, it says here that, you know, we have 2 overloads of this function. We have erase, which takes in an iterator, or potentially a constant iterator, or now a constant iterator. And we have the other version of the function, which takes in a first and a last iterator, so it takes in a range. And so what we're doing now is that we're running this first one here that just takes in 1 iterator. And the problem with that is that it says that the iterator for pos must be valid and dereferenceable. Thus, the end iterator, which is valid but is not dereferenceable, cannot be used as a value for pos. Yeah, and then it says afterwards that the iterator first does not need to be dereferenceable if first is equal to last. Erasing an empty range is a no. So essentially, what they're saying is that for this function that just takes sort of 1 iterator, you're not allowed to send in sort of the end iterator, but for the other one you can send in the end as long as that is the same as the first one. Which is a problem because we are returning, you know, a weird iterator from our remove if, which sort of just fucks up everything. So what we have to do here is that we also have to send in a.end as the second parameter, and then we'll get sort of the correct result. Questions?
Did everyone follow that? No is a valid answer here. No is preferable answer.
Yeah.
Oh, as well.
Okay. So where did people fall off?
Just mention, just say it. Now's the opportunity, just
Yeah.
to ensure that you understand it, because you may see more of that code in assignments or in labs, so it's in your favor to understand it.
Looks like C++ is like, does it have like an iterable interface or something, or how does it work?
To a certain degree, but it's not sort of the interface that you're potentially used from Java, etc.
Yeah, I'm thinking like
It's a very limited interface. It essentially has the interface that pointers has. So you know you can dereference stuff, and you can say plus plus and minus minus. On most of them, there's like 5 different categories, if I don't remember wrong. Whereas like some of them you're allowed to traverse in multiple directions. Some of them you can only traverse in one direction. Some of them have certain overloads and others does not. So, but for vector or for string or any of those that work on contiguous memory, you're essentially almost guaranteed that it's a pointer, so just straight row pointer on the other side. So, yeah. Was that an answer to the question?
yeah,
or?
because I'm like thinking
Yeah.
like the iterable interfaces in Java.
by the way, here's the picture I was showing, or I wanted to find afterwards. That sort of shows how the iterators work. So if we have a vector here, then when we call begin, we get a pointer or an iterator to the first element, and when we get a call end, then we get a pointer or iterator to the element after the entire range is done. Which is why you're not allowed to dereference the end iterator, because you don't actually know what's there. But yeah, in general, the iterator interface is like you'll see here that a lot of this says that you'll take a forward iterator, etc. I don't really get that much into the different iterator interfaces because I usually just stay with vector, and that has the sort of random access iterator tag or interface sort of, which essentially means that it works the same as a pointer does. Any more questions? So there are more benefits to using this other than sort of looking cool or whatever. Because, for instance, when we finally get library support for proper library support for all of this stuff, we'll get like parallelized versions of a lot of these algorithms. So we can run them on. You can run the algorithm on multiple threads, or potentially vectorized or whatever. But it will still to you look like it's running sort of single-threaded. Cool. Well, then I'll.
Did you go just back to the CPP reference page? So there's something. So they're marked as deprecated, right? The first signature, right? So of forward of remove until C++ 2020, it's going to be removed.
Yeah.
The top one.
It's not. It's going to be changed to being const person.
Ah, right. Okay.
So essentially, what they're saying is basically just that. Now this function sort of just happens at runtime, but from C++ 20, you can run that function in code that is also going to be executed at compile time. Cool. Any more questions? Cool. Well, all of those are sort of trivial algorithms to implement yourself, but one algorithm that isn't so trivial necessarily is doing sorting functions. So here's one showing off how that works. This sorting function is will only work on stuff like strings or vectors or arrays. It will not work on lists or like linked lists or stuff like that. Most of these functions are super generic, so that you can use them on everything, but some are sort of have requirements for their iterators, such as this one. So yeah, it's a sorting function. The cool thing about it is that it's guaranteed to be O n log n. So, and that's sort of a requirement by the standard. So you can take that as sort of the truth. It's not always that way, but usually it is. And we can use it with our sort of standard here. So we'll just do student.sort, and it actually doesn't return anything, so that's okay. And then this function also has an overload where it doesn't take in any parameters at all. In that case, it will rely on you having overloaded an operator, which I'm not super fan of. I prefer the one where you sort of are explicit in what you're sending in. So this one is, yeah, it's a compare function, which is just, yeah, a comparison function object. So basically a sort of function that takes in two types and returns true if the first argument is less than the second one. So we'll just take in left-hand side and right-hand side, and we'll just return if left-hand side is less than right-hand side. Cool. And then once we iterate over that, and comment out to remove it. then we'll see that we'll get a sorted range. And in terms of generic sorting algorithms, I would prefer to use the standard sort because it gives a good complexity, and you know, it's not trivial to implement your own sorting algorithm. However, I sort of want to stress that these aren't the sort of end-all be-all to all algorithms. It's quite possible to beat these algorithms. You just have to know something extra about your data. So sort of beating std sort is not hard if you, for instance, are just sorting integers, because then you can use sorting algorithms that like radix sort or something, which will quite quickly beat that sorting algorithm hands down. However, if you're just doing like sort of generic sorting stuff, just go to this library and, you know, try to use the algorithms library for what it's worth, because then you can focus more on your actual graphic stuff. And as you can see, there are, you know, a bunch of different algorithms here, which usually satisfies most of your needs. But that means that you have to read documentation, but that should be part of your job anyway. So is there any more questions about the standard library stuff?
What's the algorithm you use to sort again?
Hmm?
Do you know which specific algorithm is
No, it's not, because that's not specified. It's just specified which complexity it should have. But I think a lot of implementation goes for one called Tim's sort or something. But don't quote me on that, because it's a long time since I looked it up. But the thing to sort of keep in mind here when you're programming against you know, the standard library is that we don't actually have the implementation of the standard library. We just have the documentation, and then we know that the compiler implements everything that's, or should be implementing everything that meets sort of the documentation. They're actually sort of required to do that, to say that they are a C++ compiler or implementation. However, they might be doing that differently. As long as they satisfy the documentation, then, you know, that's sort of fine. So you should not be relying on stuff that isn't in the documentation, unless you know that you're only working on one platform or something. Yeah. But yeah, as you can see, you got most of the cool algorithms in here, like reversing, replacing, generating, etc., etc. Cool. I didn't show how the strings work, but you should sort of, you know, it's a sane interface and it's documentable CPP reference, so just look up how strings work.
Shall we use the opportunity, since you're switching the topic now, to take a break for like
sure.
10 minutes? Is that sensible? Yeah, so you can wake up again, grab a coffee and something. So we come back in 10 minutes.